Well, last but not least is an infamous speaker that we're going to have to. This is the last paper, and I get to do it. A little bit about my background is retired Navy submarine officer, navigator on a fast attack. Went to 3 fast attacks, and so you see some of my papers I've done for SARA. It's galactic navigation kind of papers. You know, how can I use hydrogen for galactic navigation? How can I use pulsars for galactic navigation, things like that. So that's all part of my submarine background, where we could not look outside like the skimmers do and get our GPS. We had to go figure out where we were based on sort of radio signals and things like that. So this all fits really. It's really fun for me to sit there and apply that to astronomy, which I knew nothing about before this. I also went and was a Navy's chief engineer for the UHF Follow-On Satellite Program. That's a comm satellite program. I then went on to be the chief architect for the Air Force Satellite Control Network, which is the ground stations. And then they gave me a lobotomy and made me do business development for years until I retired from Northrop Grumman. So this, I played with big antennas. I've been DoD comm antennas. But the radio astronomy really has given me a fun way to use some of the technology I've learned and apply it to astronomy, which I knew nothing about. I am a professor, adjunct professor at Webster University. I've been teaching graduate school all over the place here in Colorado. So this is all fun for me. One thing I've been trying to do is to try to apply the formulas to the radio astronomy. The goal is to use some of this data that's been collected and actually come up with ideas. That's why Kevin's always gives me good insight, because he's using advanced data calculations. So one of the thoughts here is in terms of using large interferometers like the Event Horizon Telescope. How did they actually calculate? How do they know they can go pick up the M87's black hole accretion disk? I mean, what was the basics on the physics behind how to pick that up? Okay, so as everyone knows, the M87 was the black hole that was imaged actually it was in 2017. Just for, the data was released last year. And they actually used multiple interferometers all around the world to basically make a Earth diameter sized interferometer. That actually figuring out how they figured out that would actually suffice for M87 is really what I was trying to determine with this paper here. So part of that is, what is the resolutions of, what is the size of a black hole that we can actually see, and what is the, how can you figure out the resolution of various interferometers to determine you can actually see it? Okay, so the process is, when it's define the size of observable black hole parts, you've got basically three sizes. You've got the black hole event horizon, which you can't see, and that's called the Schwarzschild radius. You got what's called a photon sphere, and I'll go over that in a second, which is basically where the speed to maintain orbit is exactly the speed of light. So it's just on the edge of the Schwarzschild radius. And then you got the innermost stable circular orbit, which is fundamentally everything else that can actually maintain an orbit around the black hole at the closest it can, that can actually, if it's with enough speed, can maintain orbit around a black hole without falling in. All right, then we're going to determine the angular diameters of the black hole parts. And then we have to go into, how do you make a synthesized beam and determine the diameter of that with various interferometers. I chose four different black hole systems. Sagittarius A star, obviously, which is our Milky Way's black hole. M87 is what they use for the Event Horizon Telescope. And then I chose the largest black hole that I believe they found, which is IC 1101. And then what's the closest galaxy, large galaxy to the Milky Way, which is Andromeda. And the goal was to see, work the numbers and see what it would take to go see those. Okay, a little bit about, and I will do this. So theoretically, there's a singularity. In other words, when everything contracts due to gravity, it all falls inside to a central singularity, which nobody knows what's in there. There's a point called the event horizon, where the gravity prevents any light from escaping in electromagnetic anything. So at that point, you can't see inside. Anything goes in will not come out. All right, so that's the event horizon. So obviously there's no light coming from this. There's no any kind of detectable radiation or anything that can leave the event horizon. So that's the edge. Then we've got what's called the photon sphere. Okay, so this is really where light. That's the first observable possibility that you can see from a black hole is where does the light speed of light actually, first time it can orbit, closest as it can orbit to a black hole without getting sucked in. So it's sort of the orbital velocity of light. So, and so that you actually see light here. Now, some of the interesting things about this is that if you look at some of the geometry on this, you can actually see light that has been circled around the black hole from the back side of the black hole. So that's some of the things you're going to see when you see different colors and different flux levels of the data, is that some of that actual flux has been sort of rounded around the black hole, and you've seen the backside of the black hole, depending on how it came in, which is really a cool phenomena. The other one is called the innermost stable circular orbit. So think of everything else, dust, whatever, all the material that happens to have an orbital velocity that is it's less than, obviously, this is where the accretion disk, this is where all the material that is surrounding the black hole is rotating around the black hole. So the innermost stable circular orbit is, I've got a stable orbit of regular material. It's going very fast, but it's between that and outwards, all that material is spinning around the black hole and it's heating up, and that's what's causing a lot of the infrared radiation and all the radiation coming from the black hole. And that's really mostly what is being observed when you're trying to observe a black hole, is the accretion disk. You also have what's called a relativistic jet. What happens is black holes are very bad eaters. They gulp, they burp. But fundamentally, as they're rotating, the magneto sphere around them is also rotating. And if they cannot suck in the material fast enough, it tends to form a beam on both sides of the black hole, which sends out this material. For large black holes, they tend to think that this is actually what prevents galaxies from getting too large, is because if all that material is entering the black hole, these relativistic jets shoot out, and they actually shoot out material from the galaxy and prevent the galaxy from growing any larger. So those are very cool. M87 is known for its relativistic jet. It's a huge jet that it has. But what I'm going to talk about here is the event horizon, the photon sphere, and the innermost stable orbit, because that's the photon sphere and the innermost stable orbit is the things we are looking at with radio telescopes. Okay, Schwarzschild. Basically, it's based on the mass of the, it's a very simple equation. It's based on the mass of the black hole. And uses the gravitational constant, speed of light, mass of the black hole, and solar masses. And you come up with the radius of the black hole. So black holes are actually relatively easy to model because they really, you can figure out the mass of the black hole, the spin of the black hole, and very quickly. So choosing my selection of black holes, I needed a couple things. I needed to find out what the mass is. I'm given the link or the papers where I got these masses, and you're going to need to know the purported distance to the black hole, and I'll show you why that needs that later. That's very important for the resolution calculations for the telescopes to understand what the distances are. If I just calculate the Schwarzschild radiuses, you see the numbers I got. And that's just for anybody who likes the math, they can follow my numbers. But what's really sort of important is this picture here. This is basically a graph of the relative event horizon diameters. Okay, so if you can see here, I couldn't even plot Sagittarius A and M31 from a size point of view against M87 and IC 1101. See the relative to sizes of the event horizons, and even Sagittarius A and M31, which is Andromeda, is so small that I couldn't even plot them against these other diameters. So one of the reasons why they chose M87 is it's a huge event horizon, but against IC 1101, it's not even close. Okay, so that's why I chose IC 1101. Is that now? By the way, it's farther away. So, but that's another story here we're going to go into. Angular diameter. Well, one thing you got to look at is in the sky, even though these things are large by themselves, they're distant. So you have to understand what the angular diameter from the observation point of the Earth is. So from that point, you need to understand the distance to the object. And this is the formula for the determining the angular diameter. If you know the object's radius and the distance, and if you use the math again, and we knock this down to micro arc seconds, and we're going to do that because that's that's 10 to the minus 6 arc seconds. That's how small we have to get in order to see these things. So if you look at it from that point of view, you understand why they chose M87. You got Sagittarius A star is actually bigger from an angular diameter point because it's actually one of the closest. It's the closest black hole to our observing point. M87 is bigger. IC 1101 is even bigger. And then you got M31 down here is actually one of the smallest angular diameters of this grouping. Okay, so that's the and so that this is one of the reasons you can see that the first thing they tried to observe is both M87 and Sagittarius A star with the Event Horizon Telescope. Okay, the Photon Sphere, I think, the most stable circular orbit. There's the big definitions for those. There is also a difference between most stable circular orbit for a non-rotating black hole and a rotating black hole. So the Schwarzschild radius is usually referred to as from a non-rotating black hole, and a rotating black hole is normally called a Kerr radius. And so, so big picture is once you determine the Schwarzschild radius, you multiply it times, assuming these are all rotating black holes, multiply it times 4.5, and I can get the innermost stable circular orbit or range, and that's what I did there. Here's sort of the angular diameter summaries and photon sphere radiuses and the angular resolutions. Angular resolutions here, you'll notice M31 is really pretty low. It's 12.5 microarc seconds as opposed to M87 and Sagittarius A star. So So the big picture is you need to get at least that small with your telescope angular resolution in order to see it. And if you want to see any definition, you better be smaller than that to see definition for these. And so here's my innermost stable circular orbit, and what the numbers are. Very similar. I mean, it's just a multiplication effect of the against the other angular diameters. Now, so if we're going to look at this thing, what is the we determine what the angular diameters need to be, and these are the I thought I'd give the astronomical right ascension declinations based using Sinbad, what these positions are, in case you guys want to do this at home. All right, so what are we looking at when we're trying to determine how much definition we want to see? And I could I put a quick little thought image here about if I wanted to view an object, that if I had my angular definition of my telescope bigger than that object, and so you assume that the object's here, and I've got a pixel that on my camera that is bigger than that object, that pretty much tells me that I will see a mixture of that central object for each pixel and the little bit of the outer area, which means that I will not be able to, I will see a blurred image or a single pixel with a little bit of signal strength against it, but I will not be able to pick out what's inside that pixel. It's only one data point. So what do I got to do? I have to break these pixels into smaller pixels so that I get multiple data points here, and at that point I can pick out multiple signal strengths against all those pixels and come up with an image that has some definition to it. So when you hear about resolving an image, that means that this is that kind of a concept, is I need to have more pixels touching that gives me different signals across that image, and so I can resolve what's inside better. So that's really sort of the big picture of the Event Horizon Telescope. How can I get my resolution down so that I can get multiple snapshots across the entire image? So I have to, in order for M87 and Sagittarius A-star, I have to get my resolution down below the innermost stable circular orbit angular diameter. All right, a little bit about interferometer beam widths. That's the formula for it. It's basically frequency over diameter, or distance across from an interferometer. It's the distance between the baseline, distance between the max antennas is your distance there. So big picture is the higher the frequency, excuse me, the higher the lower the wavelength, and the higher the radius on the baseline, the lower the beam width. Okay, so the part of the interferometer radio research was what is the capability of these big interferometers at the highest frequencies in gigahertz, and what is their maximum baselines? Because one of the things we have to do in order for the Event Horizon Telescope was I had to combine like ALMA and the European Very Long Baseline Interferometer, all those antennas together, and they all had to have the same, that'll be measuring at the same frequency, which they all were not designed to do. And then I have to correlate them with the same time because the phases have to combine. So I have a very tight timing, and I have very precise positioning and pointing, etc. And they all had to have the same frequency when they started. So and by the way, the higher the frequency, the harder it is to get that timing so their phases are reproducible and synced up. So going higher frequency causes a lot of troubles, which caused them, which is really what the innovation was for this Event Horizon Telescope is to be able to get these high frequencies to correlate by using by simply recording the data and then processing them in a separate location later. This is how you turn it into arc seconds for a half hour beam width. Green Peg telescope. What if I just use Green Bay telescope? I mean, it's a big antenna. It runs at 116 gigahertz, but it's only 0.1 kilometers in diameter, and I would get 6.51 arc seconds. That's the smallest I can get. The Very Large Array, we've all been down there, and its maximum is 45 gigahertz, and but because it is basically 27 kilometer, has 27 arrays, 36.4 kilometer max at its A configuration. I can get it down to 0.046 arc seconds. All right, ALMA's very good too. Its advantages can go to 230 gigahertz, and it can get down to 0.02 arc seconds. It doesn't have as big of a baseline as VLA does. European Very Long Baseline Interferometer. You see where a lot of those antennas are, and those are also correlated antennas. This has, if they combine those antennas, the various locations, and they run it at the these baseline. These are in centimeters, 0.7 centimeters. They can get 0.14 milliarc seconds. So they can get lower, but that's still not even close to the microarc seconds we need for the these telescopes. So we're down to 10 to the minus 4th here. So that by itself is okay. I mean, it's getting there, but it's not. I'm still bigger than the my pixel is still bigger than the object. All right. So what better telescope do? Basically, they observed this thing. Their first observation in 2017 was to get these antennas together. They did subsequent observations and added some antennas, and a couple dropped. The goal here is basically this antenna is almost the Earth diameter. That's about the max they can get, and realize also that the Earth's rotating, and part of an interferometer's capability is that it actually takes samples from every antenna in the interferometer, and then it waits and moves it again, takes another sample. So it actually is a moving picture that fills in the holes. It allows you to get that picture. So this is what they've used here. And notice that these are big interferometers that have multiple antennas themselves, but you see them as single points here. So realize that these are not just one antenna at these locations. These are multiple antennas at each location. And that's also important because you got to fill in the center. You just can't have two antennas that are Earth diameter and one north and one south, one east and one west, and expect it to fill the hole in. You got to have a lot of antennas in the interior to fill in the picture. So EHT, they did 230 gigahertz. That was what they did for the M87 shot. And if you do that analysis, you get 30.7 microarc seconds. Okay. It claims to be at 25 microarc seconds. The new innovation they're going to do is they're going to raise all of these antennas to 345 gigahertz, which will allow it to get down to 20.5 microarc seconds. Okay. So basically, this is a sort of showing at the different frequency levels and stuff what the microarc seconds. So you can see if I try to use GBT, we're at 6 million microarc seconds just by the GBT. The VLA can only go to 46,000 microarc seconds. ALMA. Now, if you start adding the European Very Long Baseline Array, 138, and then at 230 gigahertz, for the EHT current antennas, you get 30.7. When they go to 345, you get 20.5 microarc seconds. So you can actually see the how they're coming up, deriving how these antennas work. Okay, so if I look at event horizon diameters, and I look at the think of it as the pixel from your screen. How big are each of these guys? And so for the event horizons of M87, M31, IC1101, and Sagittarius A star, you see they're all down here. So there's nothing to see there. They're just, it's black, but you can see right now that the EHT 230 gigahertz and 345 gigahertz, the pixel size basically of that against the event horizon of each of these objects, you can see that they're way large. Okay, if you do that against the photon sphere, which is really the first bit of observable data you can get from a black hole, you see that the Sagittarius A star photon sphere is almost same size as the 345 gigahertz resolution. But everything else is really pretty small, right? So photon sphere is still sort of out of our ability to resolve it, though 345 is getting close. So you look at the innermost stable circular orbit and realize that that's the beginning of the accretion disk. Everything outside that is actually larger. You see that should be ISO instead of IMSO. Sagittarius A star is up here, M87, and then this is why they said the Event Horizon Telescope at 230 gigahertz is actually smaller than the M87 and Sagittarius A star innermost stable circular orbit, and that's why they were able to resolve M87 with 230 gigahertz. Now, if you look at 345 gigahertz, which is now this purple line, you see that that's almost half of the Sagittarius A star and not quite half of the M87 innermost stable circular orbit. So this tells you that when they get to 345 gigahertz, you're going to get more definition on your Event Horizon telescopes for these things. And now if you look at also ISCO and M31, you can see that the 345 gigahertz is inside the, let's see, which one's which? Okay, the ISCO, the 345 gigahertz is still smaller than the M31 and the 1101's innermost stable circular orbit. So you're still not going to get resolution from either one of those. A little bit about the, here's your telescope resolution summary, and here's your black hole resolution. So it sort of shows that anything, if these resolutions are smaller than the black hole ones, you should be able to see them. So big picture is that you've got some close, and we still got a long way to go on resolution. Okay, so M31 was the smallest of the objects I chose to be observed from an angular resolution point of view. So what would it take to make the EHT capable of resolving M31? And so big picture is in order to see it, I need to be at 12.55 microarc seconds. We saw I've calculated that before. And so if I'm going to have that, if I want to really resolve it really well, I want to have that to 6.27 microarc seconds. So how do I make a telescope capable of doing that? So first I looked at, hey, if we use 345 gigahertz, which is what they're going to now for EHT, that gives me my highest frequency. Then I calculate what it would take, what's the distance I would need on my baselines to get down to 6.27 microarc seconds. And if I know I need 35,140 kilometers, Well, it just so happens that I can't get that being on Earth, but that's almost the altitude of a geosynchronous satellite is 35,786 kilometers. So if I put a geosynchronous satellite constellation up to supplement the EHT, and I can get the orientation right, I will have enough definition to get my 140 kilometer resolution. And so that's what I'm going to recommend, is that we're going to need to have a geosynchronous satellite constellation to supplement the EHT in order to see M31 with it, with enough resolution, to see it. And then there's all sorts of other objects you can see with that resolution too. So that would work. What if I try to keep the baseline of the EHT from an Earth point of view, but I changed the frequency? What's the frequency I'd have to go to in order to see that? And that seems to be at 1133 gigahertz or 1134 gigahertz. And there's all sorts of issues with that, with timing and storage, and because your storage goes up tremendously and your sample rates and all that kind of stuff. So that actually is more of a technological hurdle than to put a couple of geosynchronous satellites up. So that's so from this sort of observation analysis, I'm recommending a constellation of geosynchronous satellites to supplement the HT in order to get the resolution for M31. The other thing you would have to worry about with a higher frequency is that you've got these radio windows from Earth, and if you look at 1134 gigahertz, you'll find that you don't have a window there. This is your visible light window. Less is worse here for resolution. So 1134 actually gives you a bad window to observe. So that's your other negative on going to that frequency. And you'd have to jump to these higher frequencies in order and hit those windows just precisely in order to see those. Maybe this bump here or this bump, and maybe you can do that. I'm saying going higher in frequency is just prone with problems with the sampling and the timing issues. Okay, summary. This is a tutorial. This wasn't meant to invent anything, even though I think the recommendation for geosynchronous satellites is a data point that came out of this. And one of the reasons they have not released the Sagittarius A-star findings is because it looks like there's a lot of stuff in between us and Sagittarius A-star, dust clouds, things like that. And it was actually not as clear of a shot as the M87. Even though M87 was smaller angular diameter, Sagittarius A-star, which had a lot of other stuff that sort of, I think, fuzzed up the image to the point where they haven't released it yet. But I think they're going to release something on that pretty soon. I see 1101 and M31 they haven't even tried yet, I don't believe. But it appears that M31 would be actually hardest to look, even though it's one of the closest large galaxies we've got. Okay, so big lessons learned on this. Black hole observations are dependent on mass and distance. Telescope observations are dependent on maximum antenna spacing and frequency. Sagittarius A-star should be easier to observe with the HT than M87, except for maybe dust blocking. 1101 and Andromeda should be able to resolved. At least 1101 probably resolved with 345 gigahertz antenna. And EHT version, but barely. And Andromeda, it's going to take a geosynchronous satellite constellation distance, and that's going to be more than just one antenna, one telescope up there, but multiples, just to get the orientation and the north, south, east, west kind of thing. I don't go in. This analysis doesn't go into observation time. The interior antennas you're going to need just to add the data to get the flux, etc. So, okay, that's all I got. Anybody have any questions? You go ahead and pipe up.
Yeah, haven't they already tried space-based interferometry? Didn't they take um, the Earth width interferometer that they've got and add the Russian radio communications satellite,
You know,
which
I
is in orbit?
I don't think the space interferometry is new. Um, if you what I'm trying to apply that to is the EHT. You're going to also, in order to get a good image, you're going to have the large number of antennas at the same frequency correlated together, and so you're going to have to somehow add that to the EHT network. That has not been done. I think these other ones, they can see something, but there's not enough. I don't think it has even though they're large distance apart, they don't have the extra antennas in between that can give the picture with a high enough resolution. So they got the angular diameter, but they don't have the detail in between. So you need sort of a combination of both, I think.
Yeah. The commercial geosynchronous satellites, their useful purpose is based upon the footprint of their radio communication, and they're all close to equatorial. If you wanted to do an interferometer, you're going to need geosynchronous satellites at several inclinations
Right.
in order to make a big array of them.
Yeah,
Um,
I would say Molniya satellites would be good to add.
yeah,
You guys have this polar satellites, but those are hard to do at the geosynchronous distances. Yeah, and it has to be right. It has to be the right angle too. So I don't think
yes.
you know M87 isn't. Those guys aren't straight up and straight down on the North Pole. I mean, so we need to find an object that we want to observe that is directly up or directly down from the North Pole in order to use geosynchronous satellites properly. So it's probably a combination of satellites, and I'll choose Molniya. That goes. That's a larger distance than
Yeah.
geosynchronous anyway. So
Why not convince the companies that are putting constellation satellites up to put an antenna outward facing?
because they're big antennas, they
Yeah.
have to have really. I mean, it is. I would say these antennas. Well, I don't know. I think we have to do design for that. I don't
Yeah.
know how big the antennas. 345 gigahertz can't be that big of antenna,
Right.
but 18-meter antennas on the ground. I probably don't need that big of one in the spacecraft, but part and now let me throw another thing out. The fact that these things are moving, the relativistic timing offsets will have to be calculated, has to be sampled. Then I have to ship all this gigabits of data down to the ground in order to be correlated with the other antennas at different snapshots. All
Yeah.
that has to be worked differently. Yeah.
Yeah, but we already know how to do that because we have GPS satellites. We know how to do the
Yep.
relativistic shifting, and they have
Yep.
atomic clocks on board.
Yep. I mean, I think no, I think mechanically and from a design point of view, I think it's extremely doable.
Yeah.
I don't know if they've done it yet.
I think they just need the money to do it.
I think so too. Yeah.
Very good.
All right. Thanks. Anybody else? Let's see. Todd, was that you? Let me see who else. Preston, did you have a question? A moon or orbiting the moon? Absolutely. I mean, I think that's why people want to put a radio telescope on the moon. That gives you that big signal. Just too bad there's only one moon. I mean, it'd be nice to have a couple of moons and in a nice orbit. So that'd be nice. Okay, I think that's
Yeah,
all the questions.
the people that want to put the radio antenna on the moon, they always say, put it on the far side of the moon where it's more radio quiet, but then you have no way of getting the data back to Earth. So you need orbiting satellites to get it back, or you need really long fiber optic cables going around the moon to, satellites on the limb.
Yeah, that's all. As an engineer, that's all engineering, right?
Yeah, that's simple stuff.
That's
You
simple
just have
stuff.
to do
That's
it.
I can throw a fiber optic line and get it over the rim of the moon, and have it beam out that way, or I could put an orbiting satellite relay it or something. all that's just engineering and money, and the money is the issue.